Hi everyone! In this video we are going to discuss the concept of electronegativity. So it sounds like a really scary word, but actually the concept is very, very straightforward. So don't get intimidated by the weird word. So let's start off by a definition. So electronegativity, which in shorthand a lot of people will write little e big N, so just be comfortable with that. Electronegativity is simply a measure of the attraction. So it's actually the attraction, so keep that in the back of your mind. It's a measure of the attraction of an atom for an electron in a bond. Okay, so that's the real definition, but for me, sometimes when I'm using that to explain it to a student, it doesn't always click, and so how I actually like to word it is that it is just how well an electron is attracted to an atom. So you kind of think of it in the reverse way, if that makes sense, okay? So the things we need to know or you need to memorize is that in terms of electronegativity, there are four major atoms that you need to know, the big major players. First of all, fluorine is the most electronegative atom. It desperately wants to have an electron come near it, and that is related to its size, okay, and its actual charge of its nucleus. And so because fluorine is so small, all the protons in its core, in its nucleus, are pulling in any electrons that are sitting around that fluorine. So there's a great attraction of any electrons, including the ones in a shared bond, to the core of that fluorine atom. So after fluorine actually is oxygen. So oxygen has one less proton in its core, but it's still relatively small, but there still is quite a positive charge. So in terms of ranking electronegativity, fluorine is the most electronegative atom, followed very closely by oxygen. Then after that, we have a tie between nitrogen and chlorine. So I expect you just to know these four. So you know fluorine's the most electronegative, then oxygen, but then nitrogen and chlorine are shortly thereafter. But overall, for the global trend in terms of electronegativity, if this is a terrible drawing of a periodic table, basically what we can say is fluorine is over here in this corner, and then we have francium over here in this corner. And so what we know is that fluorine has the highest electronegativity, and then francium has the lowest electronegativity. And so what we see is this beautiful trend where we see it increases as you go up a group or as you go across the table. And so usually what people say, or across a period, but usually what people say is it just increases in this direction. So as you go from the bottom left corner to the upper right hand corner, you are increasing in terms of electronegativity. So let's see if you can practice one of these. Out of these atoms, sulfur or phosphorus, which one is the most electronegative? And we're going to do four of these. Chlorine or bromine, sulfur or arsenic, oxygen or hydrogen. Go. All right, did you get an answer? Hopefully you did. And the way I personally would have done this is I would have started off, because I know I'm looking for my most electronegative atom, I would have started off by identifying any of my fluorine, oxygen, nitrogen, or chlorine. So any of those four. If those are there, we know for sure it's going to be the most electronegative. So right away, in our second option, I see a chlorine, so I know that's going to be the most electronegative. Skip option 3, go to option 4. And we see oxygen or hydrogen. We know oxygen's the second most electronegative atom, so oxygen definitely is more electronegative than hydrogen. So all we're left with now is sulfur and phosphorus. And if we look at another awful diagram of our periodic table, we know that phosphorus is actually group 5 and sulfur is group 6. So as we go across a period, we know our electronegativity increases. So sulfur is definitely more electronegative than phosphorus. All right, we can do the same thing with sulfur and arsenic. So we know that sulfur is in group 6. We know arsenic is group 5, but it's lower than sulfur. So immediately when we look at our trend going this way, we can automatically see that sulfur is definitely more electronegative than arsenic. Now, what does this actually mean? What does this tell us? Well, the first thing I want to do is focus in on this. We just said that oxygen is more electronegative than hydrogen. So if I were to draw out water, I would be able to label that, or I would want to label that and somehow tell from one scientist to another that oxygen is more electronegative than hydrogen. And the way we do that is by using these really cute little symbols. So you have a little delta and then a positive. So anytime you see this symbol right here, that is one person telling another person that that specific atom, whatever it's hovering over, has a partial positive charge. Okay, okay? It's partial. It is not a full charge. A full charge is what happens in an ionic compound when it's a full positive attracted to a full negative. In covalent compounds, you can only have partial positive and partial negative charges. So again, you have this negative symbol. This one indicates a partial negative charge. Now, hopefully this is a review, but if it's not, that's completely fine. So then what we want to do here is go back through using these symbols and now label our water molecule. So our oxygen, we said, is the most electronegative, so that's going to have a partial negative charge, whereas our hydrogens are more electronegative than oxygen, so these two pieces are going to have partial positive charges. So that's how we would label our charges in a water molecule. But let's look at a specific bond just a little bit more closely here. So we have oxygen and hydrogen. We just said oxygen is more electronegative than hydrogen. Well, what does that actually mean? All we are saying here is that all the electrons that are in this bond here, so however many oxygen brings to the table plus however many hydrogen brings to the table, we know for sure there are at least 2 electrons here and then more electrons floating around this oxygen atom somehow. All the electrons are going to be attracted to the most electronegative atom. So whichever one has this partial negative charge, you would know, you could draw this little arrow in there to indicate that all the electrons are traveling in this direction, trying to reach the core, that very, very positive charge of that oxygen atom. So the way we denote this is we just draw out that really cute arrow, like this. And then you put a line on the side of your more electropositive atom, okay? So the opposite of your electronegative atom. And that just indicates that all the electrons are traveling to the oxygen. Now, what that means is that the hydrogen has very low electron density around, hovering around the hydrogen, whereas your oxygen has very high electron density. So a lot of times, scientists want to actually draw that out so we have a visual representation of it. So if we were to do this properly, and I'm going to come down here, what we would do is we have an oxygen here, a hydrogen here. We're saying that all the electrons are over the oxygen. So we're going to draw something really small here, and then whoosh, really, really big over the oxygen, and then quite small here in the hydrogen. All this is saying is that the electron density is hovering over the oxygen, okay? So now, if we did this in terms of a water molecule, we could draw it out like this. Oxygen with 2 hydrogens. We said this is negative, and our hydrogens are positive. So now we know overall, instead of just looking at one bond, we know that the electrons from the hydrogen are trying to go to the oxygen. Same here, from the hydrogen trying to go to the oxygen. So when we put that all together for one big molecule, all that does is say that overall, we can draw this arrow again, indicating our dipole moment essentially, saying that all of our electrons are traveling to the oxygen. So if we were to draw this out, we would have our oxygen, our 2 hydrogens, and we would say that most of the electron density is hovering above the oxygen atom, where it's really small here on the hydrogen. So again, all these here is just saying you have a big electron cloud over that oxygen. Now, my question to you is, what if we did something like this for ammonia? So we have NH3. My question is, does ammonia have higher electron density over the nitrogen or the hydrogens? Okay, which one? Go. All right, did you get an answer? Hopefully you did, but if you didn't, that's okay. This is kind of a new skill, and it's a very odd thing to do the first time you do it. First thing you do, draw out a nitrogen. Then you want to draw out your 3 hydrogens. You draw out your structure, but you absolutely need to take into account its molecular geometry. So we know this is trigonal pyramidal because it has a lone pair sitting here over your nitrogen. You cannot forget your molecular geometries when you do that. If you draw this out with just nitrogen more in like a T shape like this, you are not going to draw this out properly, okay? So what we want to do is, in fact, I don't even want you to look at that. So what we're going to do now is we go through here and we identify our most electronegative atom. Nitrogen is definitely the most electronegative atom in this molecule. So we would say the negative charge is over, the partial negative charge is over the nitrogen, and the partial positive charges are over the hydrogen. So just like with water, we know all the electrons are traveling from the hydrogens toward that positive core of the nitrogen. So if we were to draw out its actual electron cloud, we would draw it something like this. And it would be really small here, Kind of looks like an octopus or something odd. But all your electrons are hovering above that nitrogen. So to answer the question, where does does ammonia have higher electron density over the nitrogen or the hydrogen? It is 100% over the nitrogen because it is more electronegative than hydrogen. Okay, that's the big, big part. All right, that's all I've got for you today. Take care of yourself. Drink water.